Welcome everybody to today's tinyML talk. It's a great pleasure today to host Dr. Senem VELIPASALAR, Professor Syracuse University. I am Danilo Pau, and today I will be the moderator of this talk. The title of Dr. VELIPASALAR presentation is MicroCam, a low power and privacy preserving multimodal sensor platform for occupancy detection. But before to leave the floor to Senem, let me remember that this event, such as many other organized by the by the tinyML Foundation, these, as many other events organized by tinyML Foundation, are possible thanks to the support of our tinyML strategic partners. Let me remind a little bit who they are: AIZ, Arduino, ARM, BrainChip, Edge Impulse, Embed UR, Efficient, Greenway Technologies, Grovity, IMAX, ImageBob, Infineon, Inatera, Nota.ai, NXP, PNG, PIMIC, Polin Technology, Corvo, Qualcomm, Renesas, Schneider Electric, Sensimil, Sony, Silicon Labs, ST Microelectronics, Synaptics, Syntiant, and TDK. tinyML means also a huge community, more than 20,000 members in 50 groups in 42 countries. These give you the feeling of how spread is the community across the world, and the community is organized such that at local level held meetups. Meetups are a great event in which people can interconnect, can network, and share at local level their technical progresses. There is also a social branch of the community, which is in LinkedIn, the social reference mean for professionals, with 4K members and 15K followers. The huge content generated through the years by the events organized by tinyML Foundation can be found under the YouTube channel. Essentially, that's a super great media where a lot of content a different level is stored, and therefore I strongly recommend you to refer to it whenever you want to learn something that has been elaborated by the different contributors in the tinyML community. There is a huge amount of content, and I'm sure you will find the proper items or the proper technical and also marketing. Before to leave the floor to Dr. VELIPASALAR, let me just read her bio. Dr. Senem VELIPASALAR is a professor in the Department of Electrical Engineering and Computer Science at Syracuse University. She received the PhD and the MA degree in electrical engineering from Princeton University, and the MS degree in electrical science and computer engineering from Brown University. The focus of her research has been on machine learning, computer vision, mobile camera applications, wireless embedded smart cameras, multi-camera tracking, and surveillance systems. She received the Faculty Early Career Development Award from the National Science Foundation in 2011, IEEE Region 1 Technological Innovation Award in 2021, and Excellence in Graduate Education Faculty Recognition Award in 2014. Without further delay, I will leave the floor to Senem, and please the community enjoy her speech. Thank you.
Thanks, Danilo, for the kind introduction, and thank you everyone for joining. And I also would like to thank the tinyML Foundation and Olga for the invitation. It's a great pleasure to be here and presenting our work on MicroCam. So MicroCam is a low power and privacy preserving sensor platform for occupancy detection. So in today's presentation, I will start by motivating the problem first, and then briefly go over the limitations of existing occupancy sensor solutions. And then I will quickly go over the features and benefits and capabilities of MicroCam. I will touch upon the real-world challenges that we have faced when building our platforms and performing our integrated system testing. And as you can imagine, when you start testing these systems, it's very different to perform your experiments in real world versus controlled environments. And then I will go over the how we evaluated MicroCam, the different scenarios that we have used, and then I will conclude with the lessons learned and a summary. So what is our motivation? The biggest motivation is that heating, ventilation, and air conditioning, also known as HVAC, consumes a significant portion of energy that's used in buildings. And on top of this, much of HVAC use causes wasted energy because it's used when buildings are either not occupied at all or occupied under their maximum design conditions. So the question is, this being the case, can we perform occupancy detection reliably and efficiently to autonomously control HVAC systems and save energy at the same time? Now, there are existing occupancy sensors and some solutions, but these have some limitations, which include one or more of the things that I will go over in a minute. So many of the solutions employ sensors or algorithms that are not able to detect stationary occupants. So what I mean by this is that if you have a solution that heavily relies on motion sensors, that is problematic, because how many of us have been in a room where we are on a computer or reading something, and all of a sudden the lights turn off, and then we start waving our arms so that the lights can turn back on again. So that's one issue with the solutions that heavily rely on motion sensors. Other solutions, they cannot classify the source or the reason of the motion. For instance, if the motion is being caused versus being caused by a person versus a pet. And for the camera-based solutions, depending on the camera resolution and the algorithms that they use, they do not usually allow for embedded or onboard computation and require external processing most times. And many of the algorithms developed for camera-based systems are sensitive to lighting changes, and this makes them prone to missing detections or creating false alarms. And most of the existing solutions, especially the camera-based ones, they rely on adjustment of settings for different scenarios. And I'm going to touch upon this in a little bit. If you have a system which requires tweaking and playing with the settings very frequently, this complicates self-commissioning and ease of use by potential users. And many of the systems either do not have high enough accuracy or are costly or not battery powered and they need to be wired. Again, this takes us back to my comment about ease of self-commissioning and ease of use, because if you have to install these things in a bunch of different rooms and have to wire everything, that's gonna limit the installation as well. So considering all of these challenges, we wanted to build a platform that's standalone, low cost, and employs multimodal sensors so that we can address all of these challenges. So we have initially proposed this, and then we received an award from ARPA-E to develop MicroCam, and we had to meet several big challenges. There were stringent requirements that we had to meet. First of all, the biggest goal was to achieve very high accuracy at a sufficient size, weight, power, and cost balance. So another challenge was not relying on any external computation or cloud processing. And then the goal in terms of accuracy was to achieve greater than 99% accuracy with less than 2 missed detections per year. And by doing so, we wanted to save 30% in energy savings, provide 30% from utility bills. And another goal was to have a battery life of greater than 3 years on 3 AA batteries. The cost requirement was 6 cents per square foot. And then another goal was to have something that's almost peel and stick so that it provides ease of commissioning. So here's an overview of MicroCam. MicroCam consists of low-power AI-based or Internet of Things platforms. Each device consists of multimodal sensors that can process motion, audio, and video data simultaneously. And then one of these platforms is dedicated as a lead platform, and the member platforms can send binary occupancy results to the lead platform. So this is a standalone solution, meaning that each device is battery powered and all processing is done locally on each platform. There is no reliance on cloud or external computation. And then it has the ability to preserve privacy, which I'll touch upon a little bit later in a few minutes. So the privacy aspect, we try to address it in 2 different ways. One is that we are only sending the binary occupancy state to the lead platform. So at no point in time, any kind of data is being shared. And another thing that we have worked on is a proprietary technology, and our preliminary results show promise on images where occupants are not discernible. So here you see a prototype that we have built earlier in the project. And then at the bottom, you see a regular image over here, and then its privacy protected version. So before introducing MicroCam in more detail, I would like to go over its benefits and the capabilities that it provides. MicroCam can operate under daylight, low light, and no light conditions. And here you see some examples with different lighting conditions. And I will point this out later. The images that you see over here, the upper right corner, the 2 images, the room is actually pitch black, completely dark, and there's an NIR LED light illuminating the room. MicroCam can detect stationary occupants because it doesn't rely on motion sensors. And then it can differentiate people from pets and other sources of motion. For instance, If there are robot vacuums or fans or blowing curtains in the room, you don't want to create a false alarm because these are the things that can potentially trigger motion sensors. And as I mentioned before, it has a mode that allows protecting privacy. So now I'm going to briefly go over some features of MicroCam. So in our system, up to 8 platforms can operate at the same time, and one of them is dedicated to be the lead platform. And the target battery life for the member platforms is 3 years on 3 AA batteries. And I'm going to go over this in detail in the upcoming slides. So current battery life of MicroCam platforms is slightly over a year. And then we have done feasibility studies showing that 3 years is achievable with other processor options, which we will go over. Out of these 8 platforms, if you choose to use 8, only the lead platform needs to be wired, not the member platforms. And the platforms communicate with each other via Bluetooth. No access to cloud is needed. And they have around 20 to 22 feet and 110 by 70 degree detection range. And during installation, the suggested installation is having the height of each platform about 7 to 8 feet from the floor. So while building the system, we also implemented an application programming interface and a web-based graphical user interface, GUI. So what API does is that it lets users and other devices interact with the whole MicroCam system. So it also allows us to notify the HVAC controller about human presence. So it's a highly scalable RESTful API, and you can invoke it with simple HTTP GET calls. And you can also configure the MicroCam system through API calls when needed. So here's a screenshot of the GUI, and the GUI provides information about the whole system state as well as individual platforms. And the way it works is that the GUI together with the API that I mentioned, both of them run on the lead platform, not the member platforms. So when the system is initiated, the platforms start to appear one by one on the GUI as they start to connect to the lead platform via Bluetooth. And then I don't know if it is visible, but what you can do as the user is that you can designate one of the platforms as entry-exit platform, which I will mention in a little bit what that means. And then you can define room aliases, like this one is in the family room, this one is a child bedroom, so on and so forth. And then you can also see the status coming from each platform, whichever room they are located in. You can also do the testing of the camera and audio through the GUI. For individual platforms. This is especially useful during installation of the system for better placement of the sensors. And then, like I said, you can also perform audio testing for sensor validation. So each MicroCam, as I said, it's standalone, and each one consists of a Raspberry Pi processor, an NOIR camera, which provides visible and NIR images, a microphone, a motion sensor, and a light source. So I'll tell what the light source is for towards the end of this slide. The processor is 64-bit at 1.4 gigahertz, 1 gigabyte SD-RAM, and then there is a Bluetooth connectivity option for wireless. For the light source, we need to use a near IR light emitting diode, which operates at 850 nanometers. And the reason is that this LED is used to illuminate the room without disturbing occupants when the lights are off and the room is completely dark. So before I continue, I would like to mention something here. So some of you might be questioning why an NOIR camera instead of a thermal camera, right? So the reason behind this was completely due to budget constraints. So at the end of the day, we needed to have a platform, all of its components combined, and the number of rooms and the number of platforms that you need to use in your house, add everything up, and then you have the square feet of your home. At the end, the whole thing should not be costing more than 6 cents per square foot. So considering all of this, thermal cameras were out of picture even at scale, because it was just cost prohibitive. So we had to use NOIR cameras for that reason. So let's talk about the autonomous occupancy detection that's being performed on each MicroCam platform. So what we did is that we modified a lightweight neural network so that we can run it on the MicroCam platforms. Just to give some general idea about the network, it's, as I said, it's a lightweight one. The parameter size is about 22 megabytes. It requires about 1.3 gigaflops floating point operations. And what we did was that we first took an original lightweight detection model, and then we collected 2 sets of test sets ourselves. So I call these first test set and second test set on this slide. And then we just tested the model just to see how it's performing on these test images. So originally, as you see here, the accuracy on the first test set was 87.56%. And then on the second test set, it was 77.7%. The first test set I'm talking about contained a total of 2,429 images. So about 1,300 of those images were images that we captured that contained people in them, and then the rest were negative images that did not have people in them. And the second test set had about a little over 2,700 images with people and a little over 1,100 images with no people. So just to give you an idea, so these are some example images from the first test set. And as you can see, the environments in this, the environment here in general is a little less complex compared to the second test set, which contained images from actual apartments. So maybe that's the reason where the performance of the original network on the first test set was much higher than the performance on the second test set. So obviously this performance was not enough for our purposes, because our goal was, the requirement for us was to have an accuracy over 99%. So what we did was a couple of things. So first of all, in addition to designing and training a neural network for visible RGB images, we also trained a neural network for low light and no light conditions for the data that's going to come from the NOIR sensor. So we, as I said, the initial performances were not satisfactory, so we fine-tuned the models. We made some modifications. We fine-tuned the models to increase accuracy. And then initially, we used almost 25,000 NOIR images and over 23,000 RGB images for this purpose. And then we also performed data augmentation, which is commonly done in machine learning to cover size, rotation, and distance variances. So here are the numbers that we have after fine-tuning. So the accuracy on the first test set went up from 87.5% to 96.37%. And on the second test set, it went up from 77.7% to 98.26%. So we are getting there, but not quite there yet. So then we turned our attention to edge cases. So what I mean by edge cases is that these are difficult scenarios which happen somewhat rarely, not always. For instance, when we talk about edge cases, we talk about things like people lying on sofa, sleeping in bed, and then sometimes they are covered under blankets. They could be wearing hats and sunglasses, and then there are different camera perspectives, distances, and so on. So first, we collected about 420 images from the internet and just performed an evaluation with our fine-tuned model. And then we realized that the people was being missed in 13 out of these 420 images. So at one point, we were doing very fine-grained experiments. I can give you an example. At one point, one of my students was lying on sofa, and then he was gradually pulling up the blanket on top of him so that we can figure out at one point the algorithm starts to fail, if it's gonna fail. So here are some observations, conclusions that we have arrived. Maybe I should keep calling it observation. So let's divide this into two categories. So let's say you have an image and the face of the person is visible. So the other category is when the face of the person is not visible. So if face is visible, if your model can see any additional body part, in addition to the head, for example, it could be arm, it could be a leg, in general, it's able to detect the person. However, if you can only see the face and nothing else, this is one of the instances where you start to see misdetections. Now, when face is not visible, but the person is in a sitting up or torso up position, and yes, again, just to remind, the face is not visible, but at least about 30% of the body is visible, then the algorithm still is able to detect the person. If the person is lying down and the face is not visible, meaning the back is towards to the camera, then this also is a scenario that's likely to create misdetection. So after this experiment, we kept collecting more data. one set of data contained about 215 images, again, for extremely hard and relatively rare cases. At one instance, for instance, when my students presented me the first two images, at first, I didn't even realize there were people in them. I wasn't looking that carefully, but there's a person here. Head is covered in between the arms, and then the person is here hiding behind the sofa. But we just wanted to push the algorithm, the detection to its limits, basically. And here you see an extreme occlusion case, so on and so forth. So, but after capturing these images, we kept improving the algorithm, fine-tuning it, so on and so forth. And I'm going to talk about the final performance when I talk about the real-world tests in a little bit. Now, I would like to spend a little bit of time to talk about issues that we face during integrated testing. So it's one thing to spend a lot of time perfecting your algorithms in front of your computer. It's a completely different thing to actually building your platforms and then putting them to the test in real-world settings. So one of the issues that we ran into was an interesting one. So as I mentioned before, there is a motion sensor as well in these units, and I'm going to explain in a little bit the purpose of the motion sensor. And what was happening was that the motion sensor was unexpectedly being triggered because of the Wi-Fi signal. So the Wi-Fi signal on the platform was triggering the motion sensor, which was not a good thing, a good problem to have. And the second issue that we ran into was the adjustment of the exposure and ISO settings for the low light and no light modes, because despite having the near IR LED light, we were getting images like this one you are seeing here under no light conditions. So we had to spend a considerable amount of time to figure out what was causing these issues, and then to figure out how to solve them. So in almost most of the cases, the way you figure out an issue is happening, like you don't immediately find out what the issue is, because what you see is the system performance. Let's say the room is empty, but your system is saying it's occupied. And then you first try to find out what's happening. Is it the algorithm? And then you dig deeper, and then you realize, okay, the motion sensor is being triggered and the room is not occupied, so on and so forth. So there was a lot of debugging and problem shooting going on. Another issue, this is not necessarily an unexpected issue, this was just a fact, is that the LED light is a high power element which requires external power. And we were using a lab equipment to manually power up the LED light. But this was definitely a bulky and not stable solution, and it was very prone to human error. So what we had to, and what we ended up doing, was designing and building a power module ourselves for all the platforms, so that we can provide power from the same power line as Pi. So this is another thing we had to spend some time on. Another issue that we ran into during integrated testing was the flickering light sensor. So at certain illumination levels, the light sensor was behaving unreliably, which was causing there's a mechanical NIR filter in front of the camera, and then and that it was causing the NIR LED light to turn on and off too frequently. And as you can imagine, this is problematic because you can not only damage your filter motor, you can also damage your NIR LED light power module. So we had to come up with a solution to use the pi to filter the output of the light sensor, and then it was able to drive the mechanical filter of the camera. Okay, now let me spend a little bit time on energy calculations, and let me make a distinction between two types of energy that I'm talking about. So in this slide, I'm going to talk about the battery life of individual platforms. And when I talk about 30% energy savings, that refers to energy savings due to autonomous control of the HVAC. So that's building energy. This one is related to the power life of individual MicroCam platforms. So we have done a lot of measurements of the processor when it was idle, of the processor when it was processing, the camera by itself when it's idle, the camera when it's running, microphones, IR lights, so on and so forth. So as you can see in the first row in this table, the bulk of the power consumption is due to the processor, the Raspberry Pi. And then we have done actually quite a bit of experiments where we measured what would be the battery life if this platform wakes up and many times a day. So what do I mean by waking up? Waking up is when your system is not idle. So it wakes up, the sensors are turned on, they start capturing data, and then you process that data. So if you are conscious about your battery life, unfortunately, you do not have the luxury to keep your platforms on all the time. That's not feasible. So you have to come up with duty cycles and scheduling mechanisms so that you can minimize the energy consumption of individual platforms so they can have longer battery lives. So after designing our algorithms for autonomous occupancy detection, then we had to spend considerable amount of time coming up with these scheduling mechanisms so that we can maintain certain duration of battery life. So over here, you can see that with the Raspberry Pi, your battery life is about 367 days. And then then we started thinking about, okay, what are the solutions to this? Can we increase the battery life any further? And then we did feasibility studies by different processor options, such as processing in memory, PIM options. So with these options, for instance, if you look at the third row of the table, the power of the processor when it's idle is only 100 milliwatt as opposed to 1300, and 10 milliwatt when processing as opposed to 1200. And then the operation days goes up to close to 2000 days. And then we looked at the battery life. By the way, this is based on 2 wakes up a day. So we looked at different number of waking ups a day. And then we have found out that if you can wake up 10 times a day, and then with the PIM options, a power consumption of 16 watt hours over 3 years is feasible. Okay, so let me talk about how we tested the MicroCam platforms and the entire system in real world. So we have done 3 different sets of experiments. So we started, by the way, I should mention, most of this testing coincided with COVID. Initially, we have done a lot of integrated long-term laboratory tests, and then we had to take some of the platforms to different apartments, and we had to test it ourselves. And then there is a third-party testing that was performed, which I will talk about in a little bit. So let's start with the integrated long-term laboratory tests. So we perform tests during daytime and under no light conditions. The daytime tests lasted around 111 hours. And then in these tests, we had 100% accuracy and no false positives. And then no light tests lasted over 10 hours, and then the accuracy was greater than 99%. And here is how we are defining accuracy as the number of correct decisions to the number of all samples. So then we did tests in different apartments, 3 different apartments to be more specific. And these lasted a little over 412 hours, and then the average accuracy was 99.37%. And then third-party testing was performed under the leadership of Dr. Kristen Chetin at Michigan State University. So under the program that ARPA-E program that we were supported, there were category D teams, and they were tasked to test these platforms that were developed by different groups. So let me say a few things about the tests that we performed in different apartments. So here you see a layout of the first apartment, and then this is one of the platforms. There is a total of 3 platforms, and this one is dedicated, named to be the entry-exit platform. So an entry-exit platform, the name and the role is related to those duty cycles and scheduling mechanisms that I briefly mentioned before. Otherwise, the platform itself is exactly identical to any other platforms that you see over here. So in this case, there were no false positives, and all the people were successfully detected in the total time tested, which is about 2,800 minutes. And then the second apartment is just a single room, as you can see here. And then again, the test time was over 2,800 minutes. And then there was a duration of false positives here. And then these are the precision recall and accuracy numbers. And then the third apartment. So this one is interesting. So the total time tested here is 88 hours, and precision is 100%, accuracy is 99.07. And then let me tell you what happened here. So this apartment is being shared by 2 people, and at one point, subject 2 leaves the apartment, while subject 1 is sleeping. So normally this should not be a problem, right? But what's happening is that the person who is sleeping is here. And then, I don't know if this frame exactly corresponds to the time the person is sleeping, but that's definitely the angle. And if the person is sleeping in this position and the back is turned to the camera, then the system cannot detect the occupancy, and then this caused a false negative. So I just thought I would share this example with you. And then, as I said, as a third level of testing, a third-party testing was performed at Michigan State University by Dr. Kristen Chetin and her students. And they had this kind of residential layout for testing. But, you know, the testing was done in a way that it was, as far as I remember, it was only performed on the first floor of the house, and there were no sensors placed in the second floor. And then the overall analysis of these tests provide us the following conclusions. Mainly, this third-party testing provided good news because when we looked at the misdetections that came out of this testing, we quickly identified that none of these misdetections were due to individual platforms or the algorithm itself, but all of them were due to the scheduling mechanisms and the duty cycling. In other words, if and when we have better processors, which will allow us to do more frequent full scans of the house, all of these issues will be easily resolved. So let me quickly show you a demo of some of the experiment results. So this is just showing a daylight scenario. So I can skip some parts of this. So this is nighttime with the lights on. So here, as I said, the room is completely dark. And this is a video that puts a smile on my face every time I see it. So here he's trying to make sure the cat is still in the view of the camera. So he's giving him some treat to achieve that. And these are the privacy protected images that I was telling you about in the beginning. Okay, so this is on this slide, I talk about the analysis that was performed by one of my colleagues, Dr. Tarek Rakha from Georgia Tech. So he performed simulations for us with preliminary occupancy models. And the goal here was to figure out, so we talked about accuracy, we talked about, precision, not missing people, but at the same time, your system can generate false positives, meaning you declare that there's a person here when the space is actually empty. So we wanted to figure out how many false positives can we tolerate and still achieve 30% energy savings from HVAC, right? So we have looked at, he looked at two different things. What happens if you do 10 full scans per day versus 6 full scans per day? And then, so he found out that you can have as much as 27 false positives and still achieve 30% benchmark energy savings. So that was the idea of this study. And then we spent some time, our colleague here at SU, Dr. Don Carr, helped us with this, and then we designed and 3D printed an anticipated product, which looks much more attractive than our prototype for sure. And then this was done based on our studies where we know the entire MicroCam platform can fit in this. So the target size is 2 by 2 by 2 inches. And here you can see it to scale a little bit to have an idea how it looks like. So it can be peel and stick or has a magnetic attachment. So we just wanted people to see what this thing can look like when packaged in a better way. So in conclusion, we can have discussions as well later, but there are several lessons learned. One thing is that from our experiments, the occupancy detection algorithm is very reliable with very high accuracy. And we determined some edge cases where, it might fail, but many of those edge cases are really, really difficult ones, like some of the examples that you have seen. So we performed extensive studies testing the limits of the detection models. And then we found that, not surprisingly, processor is consuming bulk of the energy in terms of battery life. So better processor options are going to allow us, will give us the luxury of doing more frequent full scans of the house. And then with the existing setup we have, it's not feasible. Even with some of the higher end options that we looked at, it's still not feasible to perform your full scans too frequently during the day. So with that, I would like to thank a couple of people here without whom none of this would have been possible. So here you see my current and former PhD students, Fatih, Wei Yang, Jia Jing, Burak, and Jiang. And then my SRI and latent AI colleagues, Zach, Mike, and David. And my SU, Georgia Tech, and Michigan State colleagues, Ed, Chetna, Dan, Tarek, and Kristen. And of course, our sponsors, ARPA-E and NYSERDA. So with that, I conclude my presentation, and I'll be very happy to answer any questions you might have.
Thank you so much, Senem. It was a great talk, and thanks to enter in so many details and having elaborated your great work. I think there are quite many questions in the chat. Let me pick some of these in the remaining time. For example, you assume at most 10 wake-ups per day. Busy locations in a building apartment can have many more events per day, thus draining the battery prematurely. What provision have you made for this?
So that's a very good question. So obviously, so I tried to mention this trade-off a little bit. So this entire project was designed for residential homes, right? So if you have a daily schedule where there is a lot of entry-exit events happening to the house, right? Those are key. The more frequent you are entering and leaving your house, the more frequent scans that need to be performed, and that can drain your battery, assuming you don't have a great processor yet. So yes, that's a fact. So if you enter and exit your house 50 times a day instead of 10, that's definitely gonna drain your battery faster.
Thank you, Senem. Another question: what measures have you put in place to ensure constant power supply, considering your device may be used in a place with constant power supply?
Let me see if I understand the question correctly. So our constraint was that this had to be battery powered, right? At least the member platforms. So that's why we had to go through this challenging process of trying to extend the battery life. Now, if we can wire, right? If we have the luxury of wall powering all of these member platforms, then I think it's almost going to be 100% reliable. I'm being careful saying this, but if you don't have to worry about battery life and those constraints, then you can keep your sensors on all the time, or you can do very frequent scans every 10 minutes, whatever your heart desires, right? And then you're not going to run into any issues that we create ourselves necessarily because of duty cycling. I don't know if that answers the question.
Yeah, I think the question was if the power supply is provided not constantly, and if there are provisions to cope with this variability in the power supply.
Oh, the variability in the power supply. In all of our experiments, we were using regular AA batteries. So we haven't paid special attention to those kind of issues, but that's a very, very good point.
Okay, thank you. Let me pick randomly also other questions in the chat. There is a question about does the MicroCam device include analog neural network from the Mythic company adapter for imaging?
Let me see.
If the MicroCam device include an analog neural networks?
No.
No.
This is something that we have modified and fine-tuned ourselves. No, not that neural net. No.
Okay. How exactly does an external Wi-Fi signal trigger a camera-based image sensor? Microwaves directly activating the lines in the imager?
I think this question is related to one of the issues that I mentioned, the Wi-Fi signal. So in our experiments, the Wi-Fi signal was triggering the motion sensor, not the camera. Now, and this is a good question in the sense that you might be wondering, well, you said all of these things about not relying on motion sensors. we have a motion sensor, and the only reason we use it is in our duty cycles and scheduling mechanisms. Otherwise, again, if we don't have to worry about battery life, then we can keep the camera on longer and we wouldn't use motion sensor at all. Motion sensors are being used only for triggering purposes in our scheduling mechanisms. And then the Wi-Fi signal has been triggering the motion sensor unnecessarily. And that was created, and that was turning on our systems when it shouldn't, so on and so forth. And that drains up your battery life quicker.
Okay, thank you. Another question is about what did you use for the data collection, the Noir camera or a different camera? If you used or were to use another camera, do you think your model accuracy would be affected?
So for our data collection, we used exactly what we are using on the platforms. So actually, I take it back. Some of our data when we use during fine tuning and model development, it came from different resources, right? Not necessarily the camera that was used on the platform. And then for testing purposes, obviously, we were using the NOIR camera that's on the MicroCam. And I think as far as the model performance is concerned, I think the camera, the different types of camera is not affecting the detection performance, at least not in our experiments. And the model have been trained well enough and has seen enough variety. Of course, you can keep improving and training, but yeah, the model performance have been very, very stable.
Thank you. And is there any tracking or object detection involved?
No tracking, but yeah, definitely detection. No tracking. And there's a question that I just coincidentally saw. Why exclude pets? They may need HVAC as well. Yeah, that's a question I was asking as well, but that was an ask from us that pets should not be triggering the HVAC. So yeah, but like I said, it's not necessarily a binary decision. So this algorithm has the capability, if you want to identify a pet and then differentiate it from a robot vacuum, that's also certainly doable. But you don't want your autonomous robot vacuum for sure to trigger your occupancy sensors.
And Senem, do you plan to provide any information about the specification or even for sale information about the MicroCam?
So for MicroCam, we are going with the licensing strategy. So if anyone is interested in licensing the technology, so we are open to discussions, and this is a collaboration between Syracuse University and SRI International. So yeah, we will talk with our SRI colleagues and everything, but that's where we are right now.
Fantastic. I would stop here the Q&A session. We are already 5 minutes after the 1 hour slot. So thanks again, Senem, for your very great presentation and also to address so many questions. I suggest you to take your time also to address the other questions which have not been answered for sake of time. And please allow me to take the control of the slides in order to conclude this slot and this tinyML talk. So I'm requesting the control.
Yeah, thank you so much again for hosting me and everyone for joining. It has been an absolute pleasure.
Really, we appreciate your time, Senem, and the willingness to share your technical progresses. That's, I think, on behalf of the community, we thank you so much for your time and your dedication. Before to conclude, let me once again thank the strategic partners of tinyML, because they are the pillar for the community and to make sure that events like this one and can take place as well as many others. So let me remind what are the executive strategic partners, such as, trying to scroll here, Qualcomm, Sentient, the Platinum strategic partners, Embed UR, Sony, the Gold strategic partners, ARM, Edge Impulse, Infineon, Innatera, Renesas, ST Microelectronics, Synaptics, and the Silver strategic partners. Let me quickly remind all of them: iZip, Arduino, BrainChip, Efficient, Green Waves Technology, Grovity, IMAX, ImageBob, Not AI, NXP, P&G, PMIC, Polyn Technology, Corvo, Schneider Electric, Sensimil, Silicon Labs, and TDK. Thanks again to tinyML Foundation to host today's session, and Senem for your great talk. And let's meet to the next episode of tinyML Talks. Bye. Thank you.
Thanks, everyone.